if you are looking for some support for current affairs, if you are a fresher, you are a working professional, you are a repeater, but you want some support for current affairs, then I have a program for you. I have given the brochure and also the announcement video link in the description. You can watch if you are interested. Hello all, welcome back to Current Affairs Hitlist series. I am Guna Mathivanan from Offices IAS Academy. In today's video, we are going to discuss about Ice Cube Neutrino Observatory. Ice Cube Neutrino Observatory. First, we will try to understand what is this neutrino briefly. So, what is this neutrino? Neutrino is a subatomic particle. It is a subatomic particle. The size will be very, very small. So, it will be million times smaller that when compared to electrons. So, inside the nucleus, in atom, we will have nucleus. Inside nucleus, we will have proton, neutron, electron. So, this neutrino will be similar to that of an electron, but in terms of mass size, it will be very, very small. Neutrino is very small. It will not have any charge. There will be no charge. The mass of the neutrino will be very, very less or close to zero. The mass of the neutrino will be very, very less or it will be close to zero. Right? Since the mass is almost zero, the neutrinos will not react with anything. It will not react. It will not even react with electromagnetic force. So, neutrinos are kind of subatomic particles, similar to that of an electron, but it will not carry any charge. It will be very, very small. The mass is almost zero. Since the size is so small, since the mass is so less, these neutrinos, they will not react. They will not react with any other particle. It will not react to any electromagnetic force. See, it will not means don't think it will not react at all. The reactions will be very, 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 very less. I'll tell you an example. In 1 second, see, neutrinos are abundant. It is present throughout the universe. How much abundant, sir? I'll tell you in 1 second. In 1 second, 650 trillions of neutrinos are passing your body. When I'm speaking, trillions and trillions of hundreds of thousands of trillions of neutrinos are passing my body. See, when this pen is trying to pass my body will obstruct it. But if you take neutrino, the size is so small, the mass is almost zero, so it will simply pass through my body. So, abundantly available. Very small, mass is very less, it is chargeless, it will not react only. Right? Sir, what is the source of this neutrino? Right? Some cosmic events, nuclear fusion is happening inside the sun. That nuclear fusion reaction can also release neutrinos. Black hole collision can release neutrinos. Supernova, spatial explosions can result in neutrinos. Right? So, neutrinos are abundantly present. Example only I said in 1 second or 650 trillion of neutrinos are passing through our body. Just imagine that much abundance we have. But the problem is detecting the neutrino is becoming challenging because size is so small, it will not react only. It will not react. Or the reaction will be, it will not react means again don't think completely it will not react. Don't think that way. Reaction will be very, 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 very low. So in 1 second I said it will, our body is 650 trillions of neutrinos are passing through our body, right? Right. So like that, if you take in 1 year, in a specified region, in a specified area, let's take 1 kilometer area. I'm assuming an area of 1 kilometer. In my body only 650 trillion neutrinos are passing through. In 1 kilometer area, how many neutrinos will be passing through this 1 kilometer area? Just imagine. That many, we are not able to imagine that many neutrinos are passing through that area, right? maybe in 1 year you will find maximum of 10 reactions. So lakhs and lakhs and lakhs and lakhs of trillions of neutrinos will pass through a particular region, which will pass through a particular region. In 1 year, maybe maximum of 10 different neutrinos might react. So reaction is almost zero. These are the characteristics of neutrino. Please keep it in mind. Now to detect the neutrinos, efforts are going on. So in 1998 in Japan, a neutrino observatory was set up, which was called as Super Kamiokande. So Super Kamiokande is a neutrino observatory which is in Japan. So they created an observatory. In that observatory, they have stored almost 50,000 tons of pure water. And these pure waters are surrounded by a lot of neutrino detectors. So an observatory in Japan is being set up. So here you have 50,000 tons of pure water. Okay. So we know neutrinos will keep passing through every area. It keeps passing through every area. When this neutrino passes through this observatory, when they pass through this 50,000 tons of pure water, right? Maybe 10 times in a year. I said, right? In a year, there can be 10 reactions. The average, if you take, there can be 10 reactions. So we have to wait. The researchers will wait. You know what is the quantity of neutrinos passing through this observatory? Okay. So the researchers will wait. And whenever there is a reaction, they will note down and they will study the neutrinos. Right? When you study the neutrinos, that neutrino will give you information about the source. That neutrino will give you the information about the source. The neutrinos are generated from various cosmic events. So you study a neutrino, you will understand about the cosmic events and the source. But however, detection is going to be very, very challenging. So why they have 50,000 tons of pure water? You have to imagine now. Assume that I am throwing a stone which is moving at a greater speed. I am throwing a stone which is moving at a greater speed. That stone, if I throw it on water, when it goes inside the water, the speed will come down. The speed will come down, right? Similarly, neutrinos are passing through at a greater speed. It is passing through at a greater speed. These neutrinos, when it passes through this water, the speed can come down. It is more conducive for reactions. Despite of all these conduciveness, the reactions will be roughly 10 times. That means 10 reactions we can see in a year maximum. Researchers will wait and they will record that reactions. Right. So neutrinos, subatomic particle, has no electrical charge, very small mass, one of the most abundant particle, hardly interact with anything. They can travel massive distances undisturbed, because the mass is almost zero. Without any issue, it is going to travel. Right? They have very little interaction, so it is difficult to detect. We have different flavors of neutrino. These neutrinos, when they pass through different regions of the space, slight changes will happen, which we are referring it as flavors of neutrino. Right. Now, I explained about the Super Kamiokande Observatory in Japan. Now, the news is about Ice Cube Neutrino Observatory. This Ice Cube Observatory is in Antarctica, this Antarctic region. It's an initiative of various universities led by a US university. Okay, so they have an observatory in this Antarctic region where thousands of sensors are kept 1.4 kilometer beneath the ice. So this Antarctic region has solid ice 1.4 kilometers beneath. 1.4 kilometers beneath the ice. Thousands of sensors are kept. Ice is the purest form of solid. Okay, in the Antarctic region, that ice is one of the purest form of solid. In Japan, they took purest water. In the Antarctic Ice Cube Neutrino Observatory, they took ice only, naturally available ice. So almost imagine thousands of uh, detectors. Okay, so thousands of sensors, they have been kept almost 1.4 kilometer beneath the ice. Here we have ice. Beneath that 1.4 kilometers, sensors have been kept. Why? To detect if there is any reaction. Neutrinos will be passing through. Any reactions, that will be detected. But in a year it will take, maybe maximum of 10 reactions we can see in a year. So scientists, they have to wait for the reactions. Now why it was in news? The scientists, they discovered one flavor of the neutrino called as tau neutrino. We saw three flavors, right? This is tau neutrino is one flavor. That was detected by the Ice Cube Neutrino Observatory. That is why it was in news. These neutrinos are very difficult to observe and detect, and they are also called as ghost particle. They are also called as ghost particle. Right?